Hey there, welcome back. I know it's been a long time since I posted a video. Um, it's 2026, guys. Happy New Year to every one of you. And I guess we are just hitting 3K. So this video is basically, I was motivated to make this video because, like, literally, um, how do we say this? But I can't find the words to explain that. But I'm so happy that after 2 years. This channel is still up to date and it's still there, and I can't lie to you guys. I'm checking out the comments and I just can't find the words, but um, just thank you so much, guys, for the support for over the last couple of years. I started this with the intention of just um, how do you say this, but I've started this just with the intention to share videos with my club members back when I was in university or in college or whatever. So I didn't thought that many people would be interested to watch my videos and specifically understand exactly how I approach things. So I'm super happy. I'm just super happy that many of you are actually using the content and the resources in this channel to grow up. And I've had actually a great amount of messages from you guys, especially in Discord or in private or whatever. Just um, I'm just so happy when I read the comments that people are growing up and understanding and making sense of what they are doing. And if a single video of my videos is helping you, then that's my honor actually. I'm just super honored to be the one that is in charge of making sure that every one of you is actually making sense of what happens around him. Yeah. So we're gonna be continuing today, guys, with the reverse engineering series of the Android. And I know it's been a long time since I posted a video around Android specifically. And I know also that this series started with the 6 videos, if I remember. I think the last video was, if I'm not wrong, if I'm not wrong, the last video I need just to check out the channel, or maybe we don't need that. I think the last video was about Frida, and we were actually practicing some CDF or something like that. So yeah, so that was the last video. So if you are completely new to the channel, you just need to make sure, as always, just check out the reverse engineering track just to understand exactly what the reverse engineering is about. And then once you've had a great foundation around the reverse engineering, then get back to this video or to this Android series so you can understand exactly also what's happening with the Android. Well, 6 videos is nothing, so there's a lot to come. So there's a lot that is going to be uploaded around this series. So you just keep that notification bell on just to make sure that you get notified when a new video is uploaded. But there is a really interesting thing occurring actually with the Android right now, is that a lot of companies are actually giving a lot of attention to mobile security, and we are actually, if you are searching for a job or an internship or whatever, then actually mobile security is a great field. So if you want to involve yourself, I'm sorry, in cybersecurity in general, and you want to pick a topic or a target, then mobile security is a great topic to be approached. So you need to be able to approach mobile security in a great way. So that's why this series of reverse engineering of Android is going to be really helpful for you today, just to help you understand exactly what's happening around Android. And as you know me, I always start things from scratch, and I always love to mix between theory and practice. So this video is going to be more theoretical, so we're going to be exploring some interesting topic, which is routing. So we have I think we did a video about routing devices or routing Android devices, but we never understood exactly how it's done. Now this is the real magic, so we're going to be exploring exactly how Magisk is doing it. So Magisk is actually the little guy that we have in here. So if you go up in your phone, we use it to root the phone. So that when we go and we type in ADB and we type in devices, we see that we have an emulator. When we get inside of it, we see that if you say, for example, who am I? Saying that we show, and when we press ensue, now it's saying that shell was granted, and if I run the same command twice, now I'm root. So how it is doing it, this is the question that we will be trying to answer today in this video. Okay, so I'm gonna be just uh, starting quickly to just say a few things so you can follow up with me. So to understand exactly how Magisk is doing it, so we need to understand few things, and I would like to call them foundation. So we need to understand exactly how does the Android is booting the operating system, and we need also to figure out exactly what is the relationship between the components that we are going to be talking about, especially the components of booting. So how does the Android boot, and what are the component of booting, or the stages or the steps or whatever that the Android is doing to boot. And once we understand those, we are going to be trying to approach this in a way that we are going to try and attack the routing mechanism, or I'm sorry, the anti-routing mechanism, or way that Android is implementing to prevent people from getting root on their devices. Okay, so I'm gonna be just opening up notes. We can either use Codium, or I think I'm gonna be using Codium. Okay, so by the way, I just cloned the Magisk repo, so we can explore on it directly later on how things are working. I'm just gonna be referring back to the code just so we can understand exactly how it's doing it. By the way, there's a lot of code that is written in Rust, but we don't have any issues with that. We've been used to any kind of programming language. So as a reverse engineer, you don't care a lot about what's the programming language that is used, because you have the foundation. You know exactly. When you just have the foundation, just more than enough, and especially in programming. So any kind of piece of code that we are going to be exploring, we always refer back to the documentation and Rust in case we wanted to understand exactly what this line of code is doing exactly. Anyway, um, so okay, so we're gonna be starting from this point, guys. So we want to understand exactly the Android security model that is implementing for the booting process. Okay, so before we understand how to break into this building or this phone or whatever, so we need to first to understand how the Android is protecting it. So there are different walls of protections or different layers of protections that the Android is actually implementing for this one, just to make sure that we are preventing unauthorized access on the dash system. For example, when we type in shell and we want to, for example, cat dash system, whatever, I don't know, what kind of things can we suppose? Well, Bill, I think it can we. Well, this one is we don't have the right to read it, but I suppose with Sue we can. So system dash build dash prop. Okay. So now we can read it. Anyway, so whatever. I want to just understand exactly first why we don't have the accessibility on this one, because it's permission denied unless we became a root. So uh, I want to know exactly what are the layers that the Android is actually implementing to prevent the unauthorized access, for example, to this file. So there's something, guys, that is really important. The first step that the Android is actually implementing to make sure that we prevent unauthorized access is bootloader. So there is something that is called bootloader. So I'm gonna be just going back. So I wanted to find a way on how I can write on the steps, because I'm actually dumping them from my head to you guys so I can explain them for you. So What's the best way to do this? I'm gonna be using Codium, I guess. Okay, new file. New text file. Yeah, okay, new text file is good. Okay, steps that Android is taking to protect from unauthorized, unauthorized, uh, sorry, unauthorized, unauthorized, unauthorized access. Yeah. So the first thing, there is actually just locking the bootloader. So okay, the question that rises here, what is a bootloader? So we go back and we just Google up bootloader, what is a bootloader? So there's a picture in here. So when you press the power on of your phone, actually there is a ROM code. So actually um, it's actually a code or a piece of code that is inside of your hardware of the phone that is going to be booting up the device and then just giving the mission to the bootloader just to boot up the kernel. So what it does actually is what the Android is actually doing in the booting process of your phone is that um, there is a bootloader and it's actually locked, and it's actually a program that will be running before the Android itself starts. And what it will be doing, guys, is it will be checking that the operating system hasn't been modified or tempered, and it won't let you boot any modified software unless the bootloader is unlocked. So so it's more like a bodyguard or something like that when you go into a casino that is checking out if the members or if the people that are entering the casino are actually in legal age or actually having the permission to get into the casino or not. And if you remember, guys, that correctly, when we want to actually to check out the integrity of any kind of software, we usually use signatures. So we try to sign on the software um, that we want to actually load or execute inside of the system, and we sign it with a private key, and then we send with it the public key and the signature and the message that we want itself, and then we check out if this program is actually uh, signed with the private key that we have or not, which means that only the people who have the private keys are able to execute that program. Anyway, so the bootloader is actually locked in Android, so which means that if we want to run anything inside of the Android phone that we have, we should be unlocking that bootloader. Anyway, this is the first step that the Android is taken to prevent from the unauthorized access, which means that uh, the which means that if we want to break the security that is implemented by Android, we need to first unlock the bootloader, and then once we unlock the bootloader, we can, for example, load a modified program or something like that. The second thing that the Android is doing after locking the bootloader is verifying the boot, which means that the system will be actually verifying every file in the original bootloader that is in there. So the second thing it's going to be doing is it's going to be verifying the boot, which means that it will be actually uh, verifying the bootloader. Uh, we can actually, I don't know, compare signatures and I don't know, checksums maybe also can be used to verify the integrity and stuff like that. It's more like e fingerprinting, so printing the system files, which means that it will be checking out the partitions and checking out the files that the bootloader will come with. By the way, so there might be a great question that is can be asked by some of you who are just watching the video. Uh, what do you mean exactly like by partition? What do you mean exactly by file system? What are you even talking about? Say, okay, you told us that there's a bootloader and the Android is locking it, and the bootloader is basically just a program or a piece of code that is going to be um, loading the kernel and uh, the different component that the operating system will need. Okay, we got this, but what do you mean exactly by verifying the system files? By verifying the system files, I actually mean that, for example, anything that is in the partition dash system, or for example, in this dash system, should be verified, which means that it's not tampered by anyone. And then the third step that the Android will take actually is it's going to be um, installing the security enhanced, which is the security enhanced of the Linux. We will actually will see this a lot, especially if you dive more inside of the Android. So the security enhanced of Linux, so is this little guy. So when a process is actually called inside of your phone, it's going to be passed by the security enhanced Linux, the SE Linux, and the SE Linux has a bunch of policies, and it's going to be asking your process, hey, do you have the access to this one? If so, then you will be granted the access to the resource or not, or whatever. Um, so it's more like a security system that controls what each program can do and what it cannot do. And by the way, even if you run the security enhanced Linux as root, the security enhanced Linux can block dangerous actions, by the way. So the policies are defined at the beginning of the starting of the operating system, which means that once the Android is fired up and the policies are set, then certain policies cannot be changed. So this is something really important because Magisk later will play on that, will play on those policies. So just keep that in mind. And the final step, or the fourth step, um, that the Android is taking to protect from unauthorized access, which is the read-only partition, which means that you can only read certain partitions, which means that system files, uh, system files, uh, actually um, can be all stored in one partition, which is, for example, dash system in this case, and there are read only, which means that they can only be read once. So this is basically the four steps. These are the steps that are taken by Android to make sure that you are protected from unauthorized access, which means that when a process tries actually to uh, get root on a certain degree, then it needs to be breaking all those steps at the startup of your phone in order to be able to get the root. Now I'm gonna be just now trying to talk about the booting process of your phone. So what happens is that the first step you press your on button, or you just keep on pressing that on button on your phone, and what happens is that the CPU will start, I guess, will start and will get fired, or will get fired, and actually once it gets fired, it will be executing. It will be executing. It will start executing actually. It will start executing the code from your ROM, which is the memory that is inside of your phone that contains a code that is shipped with your phone that contains the code that will start up your phone, and it's read only, by the way. So and then the bootloader will wake up, and then we will actually have to locate exactly the special partitions. So this is where the bootloader will start working up. So bootloader works, and it will be actually trying to locate the dash system, or let's say the system partition. This is why the bootloader is really important, guys, because the bootloader is the guy that will be actually trying to set up the things for you. So if you try to approach this or think about it, if you can attack the bootloader, then you can actually um, you can actually do a lot of things to your phone, especially in the rooting process, because now we are just actually just taking the booting process just from the perspective of someone who wants to know exactly how the boot is happening from a high level perspective. Always I'm speaking always from a high level a high level perspective, I'm sorry. Yeah. So and then what will happen, it will be checking if the boot image, there's something called boot image, is signed correctly. So I'm gonna be just taking a look at what the boot image, Android boot image. So this is an image actually that is inside of your phone. Is there like anything? Okay. Anyway, so you can imagine this boot image as the image that contains the operating system itself, which is the Android, the different partitions that we need, and all of that. So we make sure that the bootloader is actually working well. So what's gonna be happening? It's gonna be loading that Android image to your phone. Uh, but before that, it's gonna be doing certain checks, which is actually uh, really making a lot of sense to us, because as we said, as part of the Android security model, we just make sure that we are preventing unauthorized access. Then we need to make sure that we are verifying the Android image that we are loading, which makes sense. Anyway, so the third thing that we should be also caring about is now, okay, if everything is alright, so if everything is alright, then actually we load the image into memory, and by memory we say that we have a RAM. Now we load that image inside of the RAM. Now, next thing to do now, once the image, well, okay, I'm gonna be just moving on to the next step, which is the kernel. But okay, the boot image can actually, I don't know if I'm gonna be just defining this for you guys, so you can have just a look at what the boot image is having. So if there is like format, uh, well, this is what a boot image is about. So this is a recovery image. So just with from a binary perspective. But yeah, so this is what a boot image is having. So there's boot header, we have a kernel, and we have a RAM disk, and we have vendor boot header, and we have vendor RAM disk DTB. So this is a vendor boot image format, and this is a boot image format. So next thing, so we're gonna be having, so we have the kernel, and which actually in this case gonna be the Linux kernel, because we have extended the Linux on Android. We know that, so we know that from the introduction video. So which is actually the core. And we also have the RAM disk, as we saw in the image, which is actually containing the initial file system that we have, and some other, I think, temporary files. So this is what the boot image will be containing. So we have the RAM disk and the kernel. So, and the bootloader is actually going to be making sure that all the files that are inside of this boot image are signed correctly by the vendor or whatever, who is the guy that will be creating the phone or shipping the phone to the people. Anyway, so this is the boot image, and then what happens is we have a kernel start. So okay, sorry. So we have the kernel start. So uh, okay, so the kernel starts, and the first thing that will be happening is that the kernel will initialize the hardware, and then it will be mounting that RAM disk, which is mounting that RAM disk, which contains the file system and the temporary files. And by the way, guys, I'm gonna be just one last time just explaining partitions and file system for anyone who doesn't understand them. You can imagine file system. First you need to understand that everything in your system is partitions. So you have a hard drive that is partitioned. So that's why when you try to boot up a new system, if you go into your BIOS and then you go do all the steps, you came to the point where it's asking you to create partitions, and those partitions are actually like a piece of lands. You can imagine them like a piece of lands, and each file system is going to be actually like a rule inside of that piece of land. So if we have a partition called system, then we have system, we have vendor, we have different partitions. For example, in this case, if you take a look, and no, like not my own system, but if we go inside of the phone, I'm sorry, uh, we are already inside of the one. Okay, so we have vendor, we have system, we have different actually partitions. So there are system partitions and there are user partitions. And we have like a lot of partitions in Android, and each partition is actually about something. But uh, it's really important to understand what the partition is and what a file system is, and what is the difference between a partition and a file system. It's really important. So file system, as we said, is going to be the rules of that piece of land that we have created once we did all the partitions. Anyway, so we're gonna be then the kernel is will be just initializing the hardware and mounting the RAM disk, which contains the file system and all of that as the root file system, which is the dash. And then we're gonna be looking for the init, so the initialize program to execute it. And this is a really important point. This is this init program is actually the program that he will be looking for to firstly execute. So if we try to change this init file, then we can actually change a lot of behavior in the system that we are booting up. So if you want to approach it from this perspective, then this init file really important for you to resolve the problem that you are trying to solve, which is rooting a phone. Anyway, so I'm gonna be keeping on explaining the booting process steps, and then we are going to be trying to tackle how Magisk is doing it. So step four. So step four is actually the initializing the process. Now the init is going to be working, and what happens is that we have dash init, and by the way, it's the first program uh, to be run. And usually this program just have a PID of a process ID, I'm sorry, of 0x1 or something like that, if I'm not wrong. Maybe I'm wrong, just to have to make sure. You can just check out that in Google or the internet or whatever. But usually it's the first process that your phone is going to be spawning up, and then it will be reading a config file uh, from the initialize.c or rc. I'm not sure. I think, let me just make sure that one. Init.rc. Yeah, it's init.rc. Yeah. Let me go back. Scripts. And then it will be mounting. If I'm not sure, yes, it will be mounting the real system partition. And then what happens is that we have now the dash system, we have the dash vendor, the different like partitions that we have. So you can just have a lot of ones in there. So and then it sets up the SE Linux security, and it also starts I think the initial services, the essential services and daemons or whatever. So for the system. So this is what happens as an initializing process, and then we have now the next step, which is it's gonna be handing out to the zygote. So this zygote is actually a hero under the hood. I would just call it a hero, but it's doing pretty much a lot of work behind the scenes when you spawn an application. So zygote, not this one. Okay, yeah, zygote in Android. So basically, I like this picture, but this is an attack on zygote. We don't need this one. Yeah, this one. Yeah. So when the process A and B and C, whatever you spawn any kind of process, what happens is that the zygote will be the one that will be creating that process for you. So um, it's actually loaded and um, loaded with your system after just finishing the initializing process, and it loads common Android frameworks, and it's mostly doing a lot of magic in your phone. So when you launch your application, Zygote quickly tries to fork and actually just clones itself to create the application process for you. Let's suppose, for example, right now gonna be opening up Magisk. So what happens? Zygote is gonna be taking care of that, and he's basically gonna be creating the Magisk process for me, and so he's the first entry point to any kind of process creation. So that's why you need to understand exactly that Zygote is your guy there. Uh, yeah. So if we're gonna be just writing a few things about Zygote, so it's a special process that is for responsible for creating other processes. Yep. And it's actually loading. Anyway, so this is what Zygote is about. Zygote, just call it whatever you want, but it's really important to understand that this little guy is the guy that will be creating the other process for you. That's it. So, and then once the Zygote is ready and up and running, now we just move on to the system server and the Android framework. So it's basically gonna be just starting the services and such as, for example, Wi-Fi guys. I don't know. Um, telephony maybe too. Whatever. I just forgot many of them. So you can just check out the services that are on Android, and it's gonna be also the getting ready the uh, Android framework, I guess, and the home screen should appear then. That's it. This is actually this is actually what the booting process is actually about. So once now we understand exactly how the booting process is happening, now we are going to be getting back to the core problem of this video, which is how the Magisk is doing is it's Magisk. It's magic. I'm sorry. And rooting up your phone for you so you can understand exactly why you are able to make Sue from the first place and be granted the root privilege, even though you are not having the authorization to do that. So we want to get a full so we want to get full full root access, which means that the user ID is 0. Just we go back in here, so just to understand UID. So to get exactly the user, so to get the UID equal to 0, which is root. So we want to get full root access, and we want to be having the ability to modify the system files, which are read only in the first place. And we also want to bypass the security enhanced of Linux that is installed, restrictions, and we face a lot of issues, guys. So those are the main targets or the main issues that we want to resolve, but we also face a lot of issues. We face actually the first thing that we are facing, as we have talked about, which is a locked bootloader. If the bootloader in the first place is locked, then we have a big issue. We need to unlock that bootloader. And we have the verified, we have the second obstacle, which is the verified bootloader, which actually verifying the bootloader by checking the signatures and the checksums and all of that. And we also have the third obstacle, which is the read-only partitions. And we also have the security enhanced Linux blocking root operations. So we need to resolve those issues. And actually, now the thing is that I think Magisk is brilliantly or in a genius way, they are actually resolving these issues. So the idea, guys, is so simple. You just have to simplify it in this way. So instead of modifying the system partitions, which are actually gonna be triggering the verification of the bootloader, we can hijack the boot process by becoming by installing or by becoming the first program to run, which actually what Magisk is doing. And then we can patch the security in memory, which actually can modify the security enhanced Linux policies that we have talked about before they get enforced. And the third thing we can do is we can use overlays by making modification appear to exist without touching the system files, and I'm going to be explaining this very well. And then we can install a root daemon which would be granting access on demand. That actually, how do we say this? But um, it's um, it's all about figuring out exactly uh, what kind of what kind of exactly what kind of system that we are wanting to check out. Yeah. So this is what Magisk is going to be doing. Just try to explain exactly how it's doing it, but we're going to be seeing exactly how it's going to be doing it. So the first thing that we should also now just take a look at is okay, we have like the bootloader, so we want to unlock it. So first things, as we said, is we need to unlock the bootloader. So usually this is happening whenever you want to root a phone, a real physical phone. You just need to go through these steps, and the first step was always to unlock the bootloader. So uh, the good thing is that you can unlock your bootloader of your phone like um, like any phone in the world can be unlocked, especially, well, I don't know exactly about the latest versions of Android, especially for Samsung or Xiaomi or whatever, but I suppose anyone can unlock the bootloader, and once you unlock the bootloader, then you would be having the privilege uh, to just get any boot image you want modified from the internet or modified yourself, and then you can just uh, bootload it, which means that you can load that boot image file that you have. Because basically what happens is that once the bootloader is unlocked, the verification is gonna be happening, that's for sure. But the thing is that now you can you can load any boot image you want. So what happens is that first step, you unlock your bootloader and then you get a boot image, and then this is where the real stuff is gonna be happening. What happens is that once you unlock your bootloader, so how we how Magisk works on the device, we unlock the bootloader. Uh, we download uh, we download a boot image, a valid one for the phone we want to root. And what happens next is we take that boot image and we drop it to Magisk. So what happens is that if we go back to my phone, so I'm gonna be opening up my Magisk, and if you go in and install, there's this little option which is select and pitch file. So basically, it's waiting for an image. What happens is that you have the ability to patch images or boot images by Magic. So what happens is that we can patch that image with Magic to make sure that we add the initial files and the stuff that we need to get ready for Magisk to make it the first, or to make it, I'm sorry, the first program to be executed inside of your phone. So this is how Magisk is doing its magic. So once you understand that, you can understand exactly what Magisk is doing. And I'm gonna be diving a little into the code later on just to explain to you how Magisk is doing it. But this is basically how it's doing it. So we need to just unpack the boot image inside of Magisk, and then Magisk will patch it, and he will do a lot of things. So he will be extracting the kernel, the RAM disk, everything. So, but I remember, if I remember that right, if we go into like scripts, there is a one that is doing it. So just remember, this is boot. Yeah, boot patch. So boot patch. Um. Okay. Yeah, it's now, and then it's unpacking. So this is how exactly Magisk is unpacking the boot image. So it takes a boot image and then it's unpacking it, and it's checking also the OS of that image, if it's a Chrome OS vendor or something else, because Chrome OS is a different case. So he needs to be taking a look at that one. So, but anyways, so he will be unpacking that image for you and then just patching it for you. And then actually, if we go back down, we see that also it's going to be doing a lot of things. Supported. Yeah, so those are the RAM disk patches. So as we said, the RAM disk is going to be containing the file systems and the different files that the Android would need, such as the dash system, whatever. So we want to make patches on the file systems before we start executing the initialize file or the initialize process or the init process. So the first thing that we are going to be doing, we unlock the bootloader to be able to make patches to the boot image, and then we load the boot image. But now we are going to be patching the RAM disk. So this boot patch is actually booting the patched image. So as we can see, he's going to be doing a lot of things. So he's doing a lot of, so he's applying a binary Magisk boot to the RAM disk, and then as we can see, um, he's literally doing some additions, and he's changing out the initialize file with Magisk in it, as we can see, and he's adding permissions to that file and doing a lot of different things. Uh, you can look at and check out in this file. Um, Now I think, okay, I'm gonna be just explaining a little. So this initialize file, as we have talked about, is the first program that your phone is going to be executing once you get to the point where the booting process is finished or is almost over. So he's gonna be executing the initialize program. So we're gonna be changing that with Magisk Init, which is another file customized by Magisk, which will actually um, make sure that we try to implement the logic that we want to get the routing process on. And then it's going to be creating another file, which is overlay D. I think this is a directory basically, since he's using make directory. And then he's going to be adding a compressed binaries, which is magisk xz stop.xz and initialize ld.xz. And then he also gonna be backing up the original RAM disk, which is ramdisk.cpu.original. And then he is going to be also storing the configuration of that file inside of the config. I think this is mostly what he's going to be doing to the RAM disk. But he also at some point he also makes certain patches, I suppose. Yeah, there are some optional patches that he does, especially for Samsung and specific other like vendors, because Samsung has a lot of security on side of their phones. So Magisk guys already are doing a lot of research on that one, and they optionally patch certain bytes directly. So those are directly inside of the kernel. So they are just hex row bytes, so they know exactly what they are doing. For example, there are certain like instructions, if I'm not wrong, like they are trying to patch. Anyway, I didn't dig deep a lot inside of the Samsung patches they have created, but yeah, so they are just patching stuff out. And at the end of it, so they are just repacking the boot image once they just apply all the patches they needed to apply, and then they just repack the boot image for you. Yep, that's it. And then once all of that is off, they just repack. Yep, that's it. Okay, so now uh, once we have the image like patched and all of that, what happens is that if we go back, now we take that boot image and we drop it into Magisk, and it will get patched, and we saw the process that Magisk will do. Then uh, we flash the image to the phone. Okay, now once we have the image, guys, that we have patched by Magisk, we flash the image to the phone so that the phone can boot actually from that image. And since the bootloader is now unlocked, we're not going to be having issues booting up to that boot image. So that's the idea behind the unlocking of the bootloader's first step. Um, yeah. So now that's that's where the magic is going to be happening, guys. So I'm gonna be trying to simulate Magisk boot. Uh, yeah, booting with Magisk, booting with the new image. I could call just the new image. The new image. Yeah. So what happens is that bootloader is unlocked. What happens is that we load the patched image. I hope you are understanding exactly what's happening. I'm sorry. So we load the patched image, and then since it's unlocked another time, so since it's unlocked, we want phone will accept it, and the kernel starts executing. And once the kernel execution starts, so uh, we have like the Linux kernel initializes the hardware, as we know, and then the RAM disk gets mounted at dash, and then we look for actually the phone will look for the init file and runs it. But wait, we actually just have we have now Magisk initialize. If we go back, where is it? Yeah, we don't have init now. We have Magisk init. So we have now Magisk init, not init. Now what's happening, guys, is that now this is where the Magisk init will be trying to take control. This is where the hijack is happening. So it's going to be the first program that is going to be run, and we need to actually take a look at how Magisk init is doing its magic. So I'm going to be taking a look at the initialize and initialize.rest exactly. And I'm going to be taking a look at suppose line. Let me just take a look at this one because mhm. Yeah, so this is where the setup of the initialize is going to be starting. So we have self configuration.initialize. So this is a bit of Rust. So if you are unfamiliar with Rust, then it's a great chance for you to just take a look at Rust. But it's not that hard to understand. So it's a bunch of ifs and else. So nothing hard to be looked into. So unsafe is basically just staying to Rust. Hey, can you just make sure? By the way, guys, Rust is a programming language that is based on the fact that it's a memory safe I can't say that it's a memory safe, but at some point, let's say it's just safe. It's a safe memory language. Anyway, so just make sure that no pointers is leaked, no memory is leaked, and whenever you have a buffer overflow, the compiler is going to be um, giving you a warning saying, "Hey, you have a buffer overflow. Can you please not make sure that you put your indexes the right way?" So this is what Rust is about, but it's actually used a lot, especially in operating system now, and even in Linux, I guess they are just converting a lot of C code into Rust. So many operating system, many projects, especially low-level projects, are now using Rust. So yeah, it's a great programming language to understand and to practice to, and to take a look too. So good luck with Rust, guys. Anyway, uh, so it's gonna be executing an unsafe code, which means that this code will not be watched by the compiler later on if it's compiled. So actually, if even this code will be raising any issue, the compiler will just ignore and compile. Either way, so yeah. What happens is that now it will be executing the process that we want Magisk to execute, which will actually give us a lot of permission or a lot of authorization over the system. So this is the goal. The goal from the first place was to play around the first program that is going to be executed, so we can hijack our own logic. This is what Magisk guys were having behind the scenes. They wanted to achieve that. So they are actually going to be checking different argument vectors, and then they are going to be spawning up or firing up certain functions or certain methods depending on which case. So this is basically what's going to be happening, and then they're going to be executing the initialize. Now there are also either suppose in this same file certain file systems, if I'm not wrong, if we go back. Yeah, exactly. I think this one's not this one's. Yes, those ones. Anyway, so those are just critical file systems that are mounted. So the proc, which is the command line, and so basically he's trying to mount those file systems. So the key action in here is, guys, that the uh, um how do we say this? But I remember, if I remember that right, if I'm not wrong, those two file systems, which is the proc, the the proc and the sysfs, they have injected. I just forgot. Anyway, so, but those file systems are gonna be used a lot. So just make sure that those file systems we take a look at. Yeah. So and later on, once he just initializes those ones and getting everything ready, I suppose the next step is to the Android initialize will continue and the system partitions will stay as read only. We're not going to be playing around them, so we're not going to be changing, by the way, that read only, but we will be trying to change a little the security enhanced Linux policies, uh, because it's really important. And then we have actually, once we have, so the Android continue the initialize. So basically in the initialize rs dot rust, I'm sorry, we have just mounted certain or specific file systems, and we also had certain logic to implement for each of these stages. uh, but that's overall what's in there, so you can check out also the code, so if you want to understand exactly line by line what's happening there. Because at the end, this video is just a high-level perspective video about how Magisk is doing its routing. But the core idea is that we are going to be hijacking the booting process, so we can spawn up the code that we want to execute before the booting process finishes. So Android will continue the initialization. I'm sorry, initialization process, and it's gonna be now getting into the daemon stars. So Magisk has a daemon, and daemons in Linux are a kind of ways that we use a program behind the scene in the background or something like that. So we will be now starting the uh, starting the Magisk daemon, which is Magisk D, like System D or whatever. So we usually daemons just end with a D, and it's actually a long background service that is defined in the I think in the core, if I'm not wrong. I think in the core. I just forgot. Okay, I think it's in the core, or is it in the native, or just forgot. Um, mm, 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 mm. So I think native source. I think it's a core. Yeah, it's a daemon.rust. Yeah, so this is where the implementation of that daemon is occurring. And if we go and check out the line 56, 69, I suppose. Where is it exactly? Yep. So this is the Magisk D uh, structure. So it's basically just having those little fields, as you can see, guys. You can just take a look at it while I just drink some water. And yeah, so basically it has a SQL connection, a manager info, a boot stage lock, module list, Zygisk enabled, Zygisk cache info, a simulator. So it's containing the structure of the daemon, and it can also, if we want to see, for example, the modules and the magic mounts. So this is basically how Magisk, by the way, is modifying the system without touching the system partition, by the way, guys. So we just check out the module. So where is it exactly? I just need to remember. So I think it's in the core too. Um, core, yeah, module to trust. Yeah, this is how exactly it's. So this is the Magisk bin inject partitions, and this is exactly how, guys, the core idea of how Magisk is doing it without touching the file system and making it read only, by the way. As we can see, so we have the Magisk bin inject partitions, and we also have um, tu- 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 tu, the bind mount. So this is how it's doing it. So it's ignoring any kind of error if a single bind mount finds kernel limitation. Don't let it break model entirely. Okay, so basically it takes a reason, a source, and destination, and a rec. So how it's working exactly? This is a question. Now, for each file inside of the ADB module and dash ADB module and dash system or whatever, guys, if you, I don't know if you have played with Magisk before, but for the guys who played with Magisk well enough and modules and tried, for example, to break the play integrity or whatever, they know exactly what kind of path I'm talking about, which is this little guy in here. This ADB. Okay, the best thing is I guess to wait a second. Yeah, this little guy. Best thing is just to go and check out the path directly to you can understand. So the dash ADB dash module, if I'm not wrong, yeah, I think it's data ADB modules. Okay, we don't have any kind of module, that's why. But usually when we have any Magisk module installed, it's gonna be in here. So usually for each file in that in this path, we're gonna be bind mounting it over the real system partition file, and the system now will see the modified files if the partition is untouched. So this is basically how it's happening. So it's gonna be binding out that path with the file systems that we have inside of the phone. So what happens is that, for example, when you try to change something inside of this path, it's gonna be changing it in the other path without touching actually the original one. So it's more like mimicking what what the system is having. And when you do dash system, for example, cat dash system build prop, what happens is that it's binding that file from actually the original system and then retrieving it back from that path, which is actually really interesting. A really interesting thing. This is how Magisk is doing it. Now, the question also can be the question that can also be asked: how exactly the routing is happening, and how are we actually getting the root access after the device boots? So now, once the device is rooted and the Magisk is already taking care of the initialization process and all of that, um, the step one that the any kind of application needs is that it needs to be running su as we have done, and we actually saw that chill access granted by Magisk. So the su binary actually, guys, will be the gatekeeper. So it's gonna be the actual client that will be actually doing mostly the magic. Well, not just doing the magic, more just the gatekeeper. So it's the guy that you should be asking out to get the root or something like that. I think there's a code inside of the Magisk about the suit too, if I'm not wrong. And I think it's in the core also. So yeah, it's in the core, Sue, and then you can just I think um, Sue.cpp. Yeah, it's written in C++, so it's an old code from 2017. There's a lot of contributors to it, but it's basically the one that will be taking care mostly of what the client is having. So, for example, the Sue client main is having the argument counter and the argument vector. So it's basically the implementation of the client itself, guys. So nothing new more than just you can imagine it as a program like any kind of program that was implemented. So yep. Um, what are the other things that we should also care about? I think if we go down a little, so We can also have functions that are connecting to the daemon, which we have. Um, Writing to a file descriptor. I would like guys to analyze this code with you, like in the stream or something, so we can maybe some days if I had time after work or something like that. We're gonna be just opening up stream or something so we can explore together more what this code is doing. But overall, like the Sue client it feels like any kind of program that was implemented, like nothing unusual or new inside of it. So if you even want to contribute to Magisk, you just have to read this code in case you want to make a contribution or something like that to Magisk directly, in case you want it. But overall, I'm just trying to take you through a journey exactly on how Magisk is doing it. So we had a great idea, by the way, on how Magisk is doing it. So yeah, we can also take a look at the daemon itself. So if you go back to the daemon, uh, so daemon most likely, not in the soup, by the way. Uh, um, Source core. Yeah, the demon of the core, the core demon. I'm sorry, the Magisk. Okay, so okay, so we have the handle. So this is basically how it's handling the asynchronous requests uh, from the uh, for example, any kind of request by any kind of application when we press sue. So, when specifically by any kind of process, we mean any kind of application. So there's a deny list, there's a super user, and there's a Zygote, restart, SQLite command, remove modules. So these are the request codes that are going to be passed to the request. So when you send a request, you basically say what kind of actions you want to do, and most likely this daemon is going to be handling requests using this way. Anyway, so it will be just receiving so a SUE request with a calling UID, and then so checking its SQLite database that is located usually in suppose data-adb-magiskdb. Maybe that path. I'm just curious. I want to just make sure that this is the path. Let's adb data ADB, I think Magisk, yeah, Magisk.db, this guy. So usually you have ADB, usually you have this little database that is actually the SQL one, that is containing actually the permissions, and if the policy is prompt, then we show that shell granted in the Magisk application. And if it's allowed, then we grant root shell just by making sure we fork a new process, and we set up a UID 0, and then we set up the Linux context, the security enhanced Linux context, just to make sure that we have a permissive domain. And I guess at the end of it, we just make sure that we execute the whatever function or whatever command that we wanted to execute, and that's it. So this is what's actually the daemon is gonna be doing. Now, I think now there's just one thing to just check out that we just also talked about in here is the security enhanced Linux, and how we have bypassed it, and then we just check just check out exactly how Magisk is doing it. So it's a really interesting thing. So we go into native, and we go into sources, and we check the security enhanced policy, and if we go and check out the rules.rust, and we see in here a lot of rules that are actually implemented by Magisk to make sure that um, we create a whole domain just called Magisk, just to make sure that we have all the permissive and we allow all the actions that we want, and this is basically uh, how things are happening. So either way, Now, there's also another interesting feature inside of Magisk, by the way, guys. I don't know if you know it, but if you go inside of the models settings, models, I'm sorry, you have in here that no model is installed. Uh, anyway, so not gonna be taking a lot of time inside of it. I think it's in here. Yeah, we have a deny list and we have a configure deny list. Usually, guys, when we want to configure a deny list, we just add up applications. For example, I have simple play integrity checker. Just to say to Magisk, can you please not launch, for example, my application, which is that application that I've been showing you, without Magisk, which means that I don't want you actually to inject anything in the memory space of my process, and especially when it's gonna be created. And if you go back a little, if you go back a little, just a little, so you can remember with me. We've talked about this little guy, Zcode. So there is something called Zygisk. You will hear it a lot, especially if you are in the mobile security field, and especially if you are involved into trying to fix, break the uh, break the integrity of the phone, which means that you want to make banking applications or I don't know, any kind of application works on a rooted device, because usually those applications are going to be checking if they are run inside of a rooted device or not. So if they are run inside of a rooted device, they're not going to be run, or they're going to be uh, rejecting being run inside of that device. Um, anyway, so what Zcode is about is it's about creating new processes inside of your Android phone. So Zygisk is basically the actual injection entry point for um, injecting code inside of Zcode. So this is what Zygisk is about. And if we go and we can also check out what Zygisk is about inside of the core. Uh, if I'm not wrong, Zygisk, yeah, Zygisk, and then we go and check out entry is there something like entry, yeah, entry.cpp, and then if we go and check out this little line at the end, which is the entry point of code injection. So basically, how it's doing it is the Android will be loading its native Android its native bridge callback, which is the native library, or the native bridge library, but it's actually the Magisk injection code. So what happens is that once injected, the Zygisk will be hooking the GNI functions. The GNI functions, as we have talked about, are the methods that are implemented in native and that you can call back from the Java side. So he will be just um, so what Zygisk is going to be doing basically is going to be hooking the GNI functions to intercept the app launches, which means that whenever any kind of application is going to be launched, so it's going to be calling Zcode. So Zcode is going to be launched, and eventually it will be trying to execute the code that was injected by Zygisk inside of it. So it will be running the module code in every application process, which means that if you have any kind of module application inside of your Magisk, it will be run alongside the memory process of the new application that was spawned. And this is exactly, guys, how Magisk is doing a lot of magic behind the scenes. You've been installing this little guy, but you've never like dived inside of it. So this is a great opportunity. So this is a great opportunity for you to just ask questions. And at the end, I just showed you a little bit of the code. It doesn't mean that we've done a deep dive inside of the code, just understanding it line by line, but it was a great thing. So, and then just after the module code is going to be injected in every application, Magisk can actually hide that using the deny list feature that I have showed you, which means that if you add an application to the deny list, uh, Magisk won't actually inject code inside of that processes inside of the application process, and this is a really interesting thing. So if you think about it, guys, Android is doing a lot of impact in our lives. So if you want to get into, one more time I say it, if you want to get into cybersecurity, mobile security is a great topic to take a look at. And it's actually an ocean. It's actually an ocean. There's a lot of knowledge inside of this field. I'm still reading and I'm still learning. And you should too. You should keep reading. You should keep learning. Um, at the end, I do believe that knowledge is built on reading, on practicing. And if you can't actually focus, read, and watch and learn, then I don't believe that Android will actually make sense for you. Because at the end, you need to be curious enough to ask more questions and try to figure out their answers. Anyway, so this has, I think, been a long video. I don't know how much time it's been. It's been since I made a video. But okay, I think this is the end of the video. I think we've understood exactly, well, at least with the 0.1%, I would love to say how Magisk been working and how routing been working in your phones. I know, many of you have been using Magisk, but never like asked or thought, how the hell is this Magisk is doing it? But I guess now you have at least an idea on how Magisk is doing it. Thank you so much, guys. Thank you so much for the 3K subscribers. Keep that notification bell on. Don't forget to share the video too, if you have, and share the channel with your friends if they want to understand exactly what reverse engineering is about. And see you on the next video, guys. Bye.